Okay, can you hear me now? Check, check, check. No sound, everyone's telling me. Any sound now? I'll just keep dancing. Any sound? Hello? Still no sound, they're telling me. Well, let's see. Let's try something interesting here. How about, can you hear the sound now? Oh, they said yeah. It's good. Working. Huh. All right, so it was working. Mm. So I just want to check and see if the sound. Make sure we get a sound check. Check, 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 check. Sound check. Yeah. Clear as water. Great. All right. So let's play a little bit more Beastie Boys as we get going here. Must be a delay. I agree. Delay. See what questions we got. Man, lots of good questions. Okay. All right. So let's answer a few. Yeah, let's put Mike D and the boys down for a second. Let's answer a few questions. Oh, I'm a big Beastie Boys fans too, Alex. So yeah, baby. Let's get started here. So I see a question from Jose. I looks like it's a column question or a question that he may have had on the homework. I'm gonna change my camera here just a second here. Yep, that's a little bit better. I move, and now I move the camera. Yeah, that's a little bit better. So Jose wants to know what row. That's a thing you use to design columns. That's like your area scale over the entire area of the column. Do we choose on the non-dimensional interaction diagram if our value we obtain based off f prime c, f, y, and gamma of rho is beyond 0.05? I think you've got a mistake. So reach out to me if you can't find it out, but I think you got a mistake because they all should be on there. No. I understand what your question is. Now you're saying that, awesome. Yeah. So Jose, if you remember what Jose is saying is that if you're designing a column, and you draw your interaction diagram, and he's using the non-dimensional interaction diagrams, they look funky like this, and he's getting a number that's like way over here. So Jose, there was a video about this at the very end of the video, and there was a video I uploaded yesterday about this, and you should watch it. But the simple answer is that there's two ways to estimate the size of the column, and the way you used didn't work. Well, there's another way. That's if it's a moment dominated column, and it's something like if you take mu over the area times h. I think that's what and you set that equal to about 0.5. You can back solve for what the area of the column needs to be. It's one of the Jedi tricks. It was in a video about non-dimensional interaction diagrams, and it's in a video yesterday. So you should go check that out if we're going. So man, here we go, baby. What else we got going on? There were a few questions I got over the emails, but I don't see any other ones going on here. Now Jacob's asking about glass loading. So on the outside of a building, He wants to know what to do with like a glass wall on a building. So if I have something that's off the page, if I have something that looks like this, and I have some columns that are here, 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 and if this wall is made out of glass, let's say this part of this wall, let's just say that part of that wall. Yes, Jacob, you would find the area, the load of that wall, and you would apply it to that column. Let's say you have a column here. Let's say your glass wall isn't there. Let's say your glass wall maybe here, and whatever your next column is, somewhere over here. Yep, you would do the exact same thing. But in this case, you would distribute the glass wall in between the two columns. So that's something that you're going to do on your project for that. Alex wants to know about, am I receiving comments turned in on our project? Probably not a lot, Alex, because it is going to be an insane amount of effort to grade these. And there you go. Tyrone, oh ho ho, Tyrone, what a question. Is it okay to not put reinforcement on a slab on grade? So what Tyrone is asking is, if I have a slab that is like your house slab or like an industrial floor slab, whatever, a slab that's like on the ground. So he's talking about a slab that's like here, like on the ground. This is the ground right underneath it. You know, ideally that slab, and hopefully it's uniform, hopefully it's not non-uniform like this, but ideally that slab is supported everywhere, right? So it shouldn't need any reinforcement, right? Well, when the temperature changes of that slab, it's going to want to shrink, and that, if it's restrained by the ground, then that can cause cracks. Also, if that slab starts to dry at the top, so it will start to shrink at the top and it won't at the bottom, and that will cause the slab to curl, to go up and curl like this. And you'd say, like, yeah, does that really happen? Yeah, it does. And then at the edges of the slab, either from the self weight of the slab, or if there's a point load put on the edge, it'll again cause cracks. Now, so Tyrone, I would recommend, there's a couple ways to, if you don't want to use any reinforcement, there's a couple ways to do that. One way is to make your slabs very, very, very small, as in extremely small. And what's small? About less than 10 feet by 10 feet. Okay, and you're going to want to put some kind of slip material on the bottom here, some kind of double layer of plastic that's going to be able to slip on top of it. You want to use pretty thick plastic, because when you make the concrete, you don't want to damage it. So you want it to be able to slip over the top of one another. So there is the slab business, but I'll tell you what I think is a better solution is to use fibers. And if you use the right dosage of fibers, and what's the right dosage, it depends on the brand. But I'm a big fan of macro synthetic fibers, which are these rigid plastic fibers. Steel fibers could be useful too, but if you use macro synthetic fibers, you can extend these slabs out pretty far. I've seen them over 20 feet joint spacings, and those little bitty fibers do a good job of handling these things. Now the cracks still form; they're just so small they don't really cause lots of trouble. There you go. There's that one. John says, in the column design videos, or in videos in general, I mentioned axial load controlled versus moment controlled. How do we know which one it is? John, one way you could do it is, what you could do is, and I thought about adding this to this video, but I didn't come up with it until afterwards. If you remember, one of the tricks I told you was to use PU over AG and set it equal to about 1, and solve for that area gross, solve for the area of the column that you would need. The other way I told you in the video at the end, no one seemed to watch it. I guess no one watches the end of the videos. That's sometimes the most important part, is the end. Is this MU over AGH? And I said to set that to about equal to about 0.5. Oh, you can't see it? All right, I'll fix that for you. Schmack. PU over AG equals about 1 MU over AGH. Okay, you know, John, you could solve both of these simultaneously for your area. Okay, solve both of these simultaneously for your area, and you can see which one controls. You can see which one gives you the larger size column, and that is the one that you're going to want to end up using when it comes to design. So there is a new Jedi mind trick based off 2 other Jedi mind tricks that we talked about before. Yeah, dude, I'm gonna kick you if you keep doing this crap, Tyrone. So don't send emails over and over and over again, okay? Let's see, Aubrey. I don't know if I saw your video, and so send it again. Send it again, please. So radius of gyration, people sending over again. I'm gonna kick you too, man. I don't know what you want to know about radius gyration. LeBron James says, how would you approach the design of columns with bending around the 2 principal axes? Have you heard about the volume interaction diagram? Sure. So thank you, LeBron. You do good work. So what they're asking about is that when you do column design, this is an interaction diagram. It looks something like this. This is moment down here. This is axial load over here. And what you have to do is you want your answer to be within that interaction diagram. Okay, so you want it to be about here. And now what you can do is you can actually do this for 2 different axes. So let's just say we derive this interaction diagram for bending about this axis. So this would be like the failure plane for this type of loading, where we have compression over here and we have tension over here. Well, I could draw another one. It may look a little bit different, not that different though. I may draw another one. I'm going to make it look a lot different, just so it's easy to tell them apart. That for this axis, compression and tension for this axis. And what's going on here, I'm going to try to draw something in 3D. I hope it makes sense. So we're going to call this one interaction diagram number 1. We're going to call this one interaction diagram number 2. And what happens is, let's draw this in 3D. So here is my 3D axes. And this is interaction diagram number 1. That's failure plane number 1. And this is failure plane number 2. Number 2. So you don't understand? That's number 1. It's right there. That's number 2. We flipped it, put it on its side, and it's here. And what happens in between is that there's an entire volume. So that's like an entire volume. That's like a surface, a 3D surface. And again, if you combine these 2 moments, if you combine the 2 locations, you have to be within that surface on the inside. And so, wow, that's crazy. How do you do that? Whoa. I'll tell you the simplest way to do that. The simplest way to do that is to do an interaction diagram for one direction, do the interaction diagram for the other direction. And if you're inside of both, then you're going to be fine. I mean, you'll be just fine. So you can develop this 3D surface, but by making sure they're inside both of these, what you're doing is you're basically assuming this is a linear line between these 2 places. Now, it's conservative what I just told you to do. I hope this kind of makes sense, what I'm talking about. And if not, I'm going to move on and you can email me about it. All right. Yes. So Jose says his area of his column, I believe, is 200 inches squared. Is it fine to increase the dimensions to 15 by 50 to change the case we're in? Jose, you're the designer, brother. You can do whatever you want when it comes to design. You just need to have a reason why you do it. How do we change the dimensions of our area? You just make it bigger. You need to make the column bigger. He's finding that he's not having good shear performance on his column. So that's what happens in life sometimes, is sometimes you have a new constraint that changes your old design. And you just have to change your design to handle that. So make your column larger. So Hamid wants to know about fiber reinforced slab. Is it okay to use fiber slab for suspended slabs? And since the fiber is so small in length, are the stresses of each fiber will be developed in the concrete? So sure, Hamid, you can use it for suspended slabs as well. I would use reinforcement bar though in suspended slabs, or I would use something called pre-metal deck slabs or pre-metal PMDF, pre-metal form deck slabs. So sometimes when you cast decks, they often do this on steel beams. So we'll draw some steel beams here, and I will put, sometimes we'll put some metal deck forms, and then I put another steel beam over here. So these things are actually made out of metal. I bet you can find them on the interwebs if you look up like PMDF or PM like manufactured deck forms, something like that. They're made out of metal. If you cast your slab out of these, just drew that in green, whatever. And usually there's some reinforcement needed up here, temperature and shrinkage steel. This acts as your tension reinforcement at the bottom, and there's some reinforcement needed up here. Now you can replace that reinforcement with fibers, and actually it can work really, really well. Or you can replace it. I do think though you still need some reinforcement steel for safety. If for some reason a column gets taken out or a beam gets taken out, you're going to want to provide some kind of load transfer between those two. So the deck forms will help with that, but I think some kind of reinforcement up there is going to help. But then you could use fibers to help reduce that. And fibers actually do a great job, an amazing job at keeping cracks small. There's going to be a video that I'm going to post coming up about that. And as far as individual, you said something about the since the fibers are so small in length, are the stress at each fiber will be developed in the concrete? It depends. You're going to want fibers that are long enough. I'm a big fan of fibers that are about 2 inches or so in length. That's about 50 millimeters. So you can figure out what fibers you like. Now, I'm not saying they're all that way, but that's about the length that you want. I've seen 1 3/4 work, and we're about to do a whole lot more work on that topic right now to try to bring people more confidence in using fibers inside their concrete. Awesome. Can punching shear occur in raft slabs that has columns? Yeah, that's a good question. Raft slabs. I think you're talking about two-way slabs or slabs with beams. That's a beam at a column. So it can happen, but it's actually really, really rare and hard to have that happen. Usually punching shear happens on flat slabs. I could explain that, but we're seeing what's going on. Oh man, Jake, thank you so much. But you don't have to be an architect to draw. But I appreciate the compliment, man. I hope you can follow it and understand what's going on. The same way to anchor the rebar of a beam is the same way to anchor the rebar of a column, I wants to know. Yes, anchorage is the same. Development length is the same, whether it's for a beam or a column or something else that you want to use. I've got several videos about development length. Those all apply, and they're all exactly the same. Kyle wants to know, is there a non-dimensional diagram for, like, I think he means a gamma of 0.85, or are we limited to 0.6 and 0.75? So I think those are in the things that I sent out. So Kyle, there is some out there for 0.9s, and there might even be some in the packets. So in the case that you're in between a gamma of two different interaction diagrams, then you can actually linearly interpolate in between them if you want to. So you could take your answer from in between like a 0.9 and a 0.75, and you can linearly interpolate between the two. That's allowed and that can be done. I didn't show that to you because that's kind of an advanced skill, but that's what you can do if you really want to dial it in. Another thing you can do is there are some software packages out there that will actually develop interaction diagrams. The one that's most common is called PCA column. I am not a huge fan of PCA column because it takes quite a while and it's iterative. It's not as valuable, I think, as it should be. I think I've got some ideas on how to improve it, but no one's ever asked me, so we've never tried to improve it. Sure. If you want to send me a link to show a 3D of an interaction diagram, that would be great, and I'm glad you use it day to day. And Jose wants to know why is it the week of the dead next week or this week? Because it's Dead Week, Jose. It's Dead Week in school. That was the email that I sent out to everybody. It's Dead Week coming up, so I wanted to use some humor. It looks like it didn't fall on you. Man, we got a karate person in here. Yeah, sure, brother. Come on and see us at our lab sometimes. Let us know. Happy to have you. Bring your karate skills too. So, oh man, what a great question. How many shear connectors are required for a PMDF to be considered a composite once concrete's poured over it? That depends. That depends a lot on the shear in the beam. I do have videos over this. They're older. They're in my simple steel playlist. You can check them out. They're all about composite beams. They're all about how to design these shear studs. What they're asking is actually to connect the beam to the concrete, use something called Nelson studs. They are actually welded to the top of the beam with a gun. So you come down there with a welding gun. You actually come down on the top and shoot it, and you create welds right there, friction welds, and then you cast concrete on top of that, and then their job is to transfer the load from the concrete to the steel beam. So that's going to depend on a lot of different stuff. Mainly though, what the shear is on the beam. And I think it's the dimensions of the slab and the dimensions of the beam as well. There's videos all about it. Look at composite beams, search for me, YouTube, composite beams. You'll find videos about it. Let's see. Yeah. So Alex is saying in the Euro codes, their minimum dimensions are about 10 inches by 10 inches. That's 250 millimeters by 250 millimeters. And we have the same thing. Well, actually, we don't have a minimum size that I know of in our US codes, but the smallest that I've ever seen used is 12 inches by 12 inches, which would be around 300 millimeters by 300 millimeters. And so I think we're in the same ballpark. What's the advantage of a composite reinforced column, I-beam, in concrete over normal reinforced columns? Composite reinforced columns. Composite reinforced column. So what a composite reinforced column is a column made up of multiple different materials. So I'm not going to draw an I-beam right now because I've never seen I-beam concrete columns used that often. I always see them to be rectangular or circular. And now in these systems, sometimes they put you can actually put steel around them, so you can actually cast them in steel tubes. Is that what you're talking about? That's what I think of composite columns. That's what I think of actually concrete cast inside some kind of steel tube. But why would you do something like this? You would cast concrete on the inside of a steel tube to keep it from buckling. That's one big reason. And the steel on the outside helps you provide strength For your concrete, that's a great reason. There's lots and lots of benefits to this. They can be very, very efficient members. One of the big challenges, though, is if you have a fire in these. Since the steel is on the outside, if you have a fire, then they're susceptible to failure. And so that's one reason why you need fireproofing outside of that. And so a lot of places this is not used, lots of different other places. So I'm not sure what else. I mean, I guess the other thing I could think of is if you wanted to use a concrete I-beam, and again, I'm just going to try to humor you, and you wanted to make that composite. Composite means it's a section made up of two different materials. So another way that you could try to make that composite is you could try to add either FRP, or you could add some other material, some kind of plates on this surface to this surface to try to strengthen it. But I'm not sure that's done that often. I think actually most of the time people don't use these types of things because they need extra fireproofing if they do. And concrete is an amazing fireproofing. Amazing. I've got a lot of videos on fire and concrete. You should check those out. I think there's 5 or 6 of them. They've been actually getting a lot of views lately. So I hope you haven't been having a fire wherever you're at. A raft slab equals a mat slab on grade. So he's talking about, I think, Simon, this is a throwback to your previous comment about punching shear. So I'm not worried about punching shear on grade. I'm worrying about punching shear in the air. Yeah, dude, let's see. How do we determine the development link spacing when connecting a slab to a girder or beam? A slab to a girder or beam. So I'm going to answer first. Yeah, let's make sure we're all talking about the same thing. So if I have a concrete slab, and I've been going with the green a lot today. If I have a concrete slab and girder together, they actually look something like this. And usually I'm going to draw another girder over here just to kind of make things a little bit easier to explain. And if I have some kind of load right here, so there is my slab, then I am going to, so there's lots of different ways to think about this. I'm going to have tension down at the bottom. It's going to try to extend. That means I'm going to need a rebar down there. And you could think of having tension up here at the top, or you could just let it crack. You're like, what? What? Yeah, if you just design it as a simply supported beam and just put steel at the bottom down here, then you'll just get cracks over your beams. Now, if you want to not let it crack or worry about that cracking, then you could design it as a fixed structure, and you would put tension up here and tension up here. Anyway, regardless, if I start to put steel in this, I'm going to have steel that goes down here, and I might go ahead and just make it continuous through my beam. And that steel at the bottom would handle that tension force. And then I would put steel at the top up here. Steel, 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 steel. Yeah, Jacob, that wasn't very good of me, brother. You better take back your compliment you gave me. Should have drawn that flatter. Steel at the top up there. And I don't really have to worry about development length in this case because it goes all the way through. It's connected. I don't have to really worry about that. When I go to design my beam itself, and I put steel in it, steel, 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 and I put a rebar cage, a stirrup around the entire thing, steel, steel, like that. That will help confine and transfer the load between those bars. That confined core will help hold those bars together. And you're like, well, you didn't talk about that in your video. Yeah, we actually don't talk about that a lot when it comes to structural design, about how that confined core can do that. But usually, since this bar goes all the way through, it transfers the load, and it's not something you really have to worry about. So I hope that answered your question. Oh man, how do we determine which steel is in tension compression for interaction diagram problem when the cross section isn't symmetric? Oh, Hayden, so you just asked an interesting question. So he said, what Hayden says is that in the columns, we've had a lot of great column talk here. Let's just say we do let's say we do something like this. Let's say we do a T-beam, or a T column. That's a column now. Happens to be a T because somebody likes it to be a T. And we have, let's just say we have compression on one side and tension on the other side, something like that. And you'd say, Hayden, that's Hayden's question. How do you know? Well, Hayden, when you do your lateral loads on a building, right? That's the ones where you draw like a frame, right? And you think about the load, the wind blowing, or if you do an earthquake or whatever else, okay? You usually think of the wind and load going in one direction, and that might cause compression on one face and tension on the other. And then guess what? The wind doesn't just blow in one direction. The wind blows in multiple different directions, and earthquakes happen in multiple different directions. And so then you would do a whole set of load cases where one would be in compression and one would be in tension. So in something like this, you actually might have to design or develop two dose interaction diagrams. You might have to do one for this case, and then you might have to do one for this case, and then you have to figure out which one actually controls for your system. So that's what you'd have to do. You have to think about your loading, look at your structure. You may have to do things twice, especially if they're asymmetric. So now Aubrey's talking about, he means a rectangular column is what he's talking about before this composite stuff with the steel beam in the middle. So rectangular column with the steel beam in the middle. So that is done sometimes on retrofit applications where I have a steel structure that may not be sufficient. And for those that are students at Oklahoma State University, if you go to Boone Pickens Stadium, which is our football stadium, hopefully we get back there eventually, and you go and you look at that stadium and you look at the columns there, the large majority of the columns are this, where they did not have enough strength as steel columns. They actually put this concrete shell around the outside of it to increase the structure or increase the capacity of the structure. What it does is it makes it not buckle anymore. And the steel can help you on the inside. But though in that case, not always. Well, yeah, I mean, if you need extra strength for some reason, you may put more rebar around it. You may put a tie around it. I've seen that happen. Okay, it's not that common, but I've seen people do that before by whatever you need to do. And the concrete acts as fireproofing for the steel beam on the inside as well. So that's another benefit. So this is done in retrofit applications, but I'd say I don't think it's done very often at all in new construction. Almost never. Manzer wants to know about pre-stressed hollow slab concrete. I think they're awesome. I think they can be great. You just have to make sure that they have enough stiffness for whatever loading, but these are like slabs, precast slabs you can make. They usually have a shear key on one side or the other for them to actually hook together. The other side's going to look something like this. They're hollow, and then you put pre-stressing strands, usually here and here. Depends. Sometimes not though. Sometimes you just have them in the center. It just depends. You don't need all those. I put way too many. You put your pre-stressing strands wherever you need them. I think they're great. I think the one challenge is that sometimes people try to make this dimension so small that you'll get dynamic issues. You'll get where people aren't actually comfortable in your building. In a parking garage, this isn't that big of a deal because when they drive over it, you hear you feel the movements and stuff like that, and people are kind of used to that. But I think inside buildings, they can be problems sometimes. So Simon wants to know, he has seen I have seen rebar welded in the field instead of tying with wire, and it doesn't seem to fail. Why is welding rebar not advised? Well, Simon, in my country, when you weld rebar together, I guess I don't need to draw any pictures of this. In my country, when you weld rebar together, you have to have a certified welder. You have to have a certified inspector in the field, and that's very expensive. There's concerns about those welded rebar failing over time. You also have to have a special grade of rebar. Now, when I say welded rebar, I'm talking about a weld that you are needing to take load for the safety of the structure. Now, I've seen welds that done in the field just to tack or just kind of hold rebar together. That's not the same thing. That's not the same thing that I'm talking about. I'm talking about a weld that is required to transfer the load. So in my development link videos, I never talked about welding rebar to transfer load because it's just rarely done in my country. Maybe it's done in yours, but in my country, you have to have a very, very special welder. You have to have a very, very specialized inspector to make sure that those are done correctly. Right. So I'm getting lots of good questions here. I am going to take a pause. I'm going to, Wallace, you're going to have to remind me to come back, talk about your topping slab. I'm going to answer a few questions that I got in before I started talking to everybody here, and one of them was if I have a building and I have a column layout that looks something like this. They wanted to know kind of how to design that or what that's all about. So if you have a situation like this where I have a beam, and this may continue in different directions. It may continue here. It may continue here. And this is like a top view. So my eye is looking down. Column, 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 beam, beam, beam. Now, if I think about my loads, one way to design this system, not the only way, but one way to design this system is to think of these, and this is what I would recommend if you're working on a project for my class, is I would recommend treating this beam in the middle as a simply supported beam. So let's zoom me out here. Pow. If I design this one as a simply supported beam in the middle, so beam, beam, and it's got its load on top of it. So that beam, you can design that. It's going to have tension at the bottom. It's going to have compression at the top. You're going to put steel in the bottom. It's going to be great. No big deal. And when you, so that's how you design that system. Now on that, you're going to have reactions. You're going to have a reaction here, and you're going to have a reaction here. Now, what that means is for these larger beams, that you're going to have something more complicated. Maybe the larger beams, you may design them to be continuous. So again, I'm going to draw a side view. So I've got a column here. Let's say the column's going to keep going, the beam keeps going, the beam keeps going, keeps going. So I'm going to design it to be continuous. We'll just draw the column, 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 beam keeps going. So this one, you're usually going to have some kind of distributed load. If we were to draw the tributary areas for this, they would come out like at an angle here, and an angle here, and then flat, and an angle, and an angle, and then be flat, something like that. So we could turn these into distributed load, some kind of distributed load on top. Distributed load, distributed load, distributed load. And then you're going to have, in this case, you would have a point load at the center. Point load. Like that. And that point load would be equal to the reaction from that beam. So that's a fine way to do it. If you designed it in this system, you might expect a little bit of cracking right here in your slab. You could put a little bit of tension steel up there if you wanted to, temperature and shrinkage steel up there if you wanted to try to keep that crack small. But that Rihanna, is I hope answers your question. If not, then ask me some more in the chat. So yeah, there you go. Now I was gonna draw. Oh yeah, I was gonna draw a system like this. Just a quick. Um, if you had a frame system and you ended up finding your moments in this frame system, this is a question I've been getting some from people. You find your moments from your gravity loads. They'll end up looking something like this. And let's just say that this one happens to be the largest, this one right here. And I'm drawing just one bay, but what I'm about to tell you can work for every single bay in an entire building. Now, what you can do with the ratio method, the ratio design method that I've talked about in a video, is that I could design for that beam right there, and I could find my area of steel versus, this is area of steel versus moment. And this is going to be a nonlinear diagram. But if I find for 1 point on that diagram, 1 point, then I'm going to use that ratio method, and I can use it for every other moment in my entire structure, as long as my depth of my beams are all the same. As long as my depths of my beams are all the same, I can use that for every single one, and I can assume it's linear. I can assume from here to here is linear, and I can just ratio it, and I can design every single one of them. If you might say, oh, that's too conservative, I don't want to do that, it's too conservative. All right, then what you can do is you could solve for two beams. This would be maybe your highest moment in your entire structure, and this would maybe be your middle moment in your entire structure. And you could use two ratios. If you don't like that, you could use a ratio from here to here, and you could use a ratio from here to here. For my project, since what's about, I'm trying to like save you some time, I wouldn't do the second one. I would do the first one. But the idea that if you take a parabola and if you reduce it into chords, single lines, you don't need very many points to reduce a parabola to single lines, and that makes your designs way faster, way easier to do. That's like extremely powerful. Even if you use software, this is a fast way that you can find all your different steel layout and check your software and make sure it's correct. And so again, this doesn't just work for this bay. This can work for every single bay in every single direction in your entire structure. That's how powerful this ratio method is. You only have to solve for one beam in your structure, or if you want to, two beams in your structure, and then make sure it's the highest moment one, and then you can ratio it from there. This works for anything. This works for even if you put lateral loads on it, anything you want. So I'm going to scroll through here and see if there's any questions from my class. And then if not, then I'll go back and answer. Let's see. What's up, bro? Thanks for saying hi, man. So no other preguntas. So we're going to move on here and see what other people got. So Wallace asked a question. He said in Singapore, if you've got other questions on the stuff I just talked about, then like get them in right now. So Wallace said in Singapore, we do a lot of ramp up warehouses whereby we do these kind of 3 inches or 75 millimeter bonded topping slabs to get the flatness or level. So 3-inch bonded topping slabs. And then he says, because they're bonded, they tend to crack somewhat due to shrinkage. Do you have any better way to construct these ramp up warehouse slabs? Okay, Wallace, great question. So what Wallace is saying is he may have a slab that's already existing. I assume it's existing, or maybe it's not quite right. Maybe it's made up of hollow cores, like we talked about. Maybe it's made up of T-beams or something else. For whatever reason, Wallace is saying, we'll just assume it's T-beams, okay, because that's pretty common in the United States to do that. So let's say I've got a T-beam here. T-beam here, and then I've got a T-beam here. Something like that. And what Wallace is saying is he wants to, they want to come back with a bonded overlay, some kind of very, very, very thin overlay that he wants to put on top to level this out. And he is going to make this sucker 75 millimeters or about 3 inches. And he wants to know, what can we do to make it not crack? Oh man, that's a tough question. So first of all, if you're in a warehouse, oftentimes these are not very stiff. These systems you're hooking to are not very stiff. That means they're going to move a lot. That means they may even move a lot differentially to one another. And if they do, then that is going to work that slab a lot, especially the joint in between where these two places are. It's going to work it a whole lot, and it will likely cause a crack to happen right there. And some kind of reinforcement across it is about all that you can ever hope to do. But there's more, just like Wallace said. This slab, this very, very thin slab, is going to try to shrink. It's going to try to shrink inwards and go this direction. Shrink inwards and go this direction. And then that again is going to have the same problem that I drew before, and that's going to cause cracks to want to form here. Okay, so those are two different distinct things, Wallace, two different distinct things. Now, number one, I would say, are you using fibers? Because if you're not, I would recommend them. I think fibers are awesome. And again, there's a video I know I keep talking about, but there's a video I'm going to post coming up that if you're a structural engineer and you're not sold on fibers after you watch this video, I would be shocked if you weren't using fibers every single place where you saw cracking. I've just been teaching my class and I haven't had a chance to make the video, but it isn't going to be long because class is almost over, because it's the week of the dead. It's almost dead week. It's almost time where we don't actually give them a lot more assignments so they can study for their final exam. Study for the final exam? Yeah, okay, but not my class. They're awesome. So anyway, I would use fibers in this. If it's this type system, if it's this type cracks, if the cracks are happening in between your two different structural systems, I would put extra reinforcing bar at that surface. You might say like, whoa, 3 inches. I don't put any reinforcing bar in there. Well, you could put it on this. You could put it on the deck. You could actually drop it and leave it right here. Put bar right here. Put mesh right here. Put it right on top. And hold it down some way. I've seen that done, and that can work well. And you can put fibers in this, and you can put mesh in this. You could put mesh just instead of at the joint here. You could put a mesh all the way down, all the way, and that can be done, and that will help this problem. It's going to be expensive. It's not going to be something that you probably want to do in a lot of different places. So fibers may be something that you want to try. If shrinkage is truly the problem for you, if it is definitely shrinkage, you can also use something called an SRA, or a shrinkage reducing admixture. And we're playing a lot with those in my lab right now, and we find that lower dosages than what they recommend actually have a lot of benefits inside the concrete. And so there's probably going to be a video coming up about that as well. So if you truly think it's shrinkage, you could use either SRAs or fibers or both, which I'm a big fan of. If it's this differential movement, then you might want to put reinforcement across this, or you could tie steel everywhere if you really, really care about that and want to know about that. Keep moving. Oh, Matt, what a question. Okay, so you're talking about torsion on a column. Can I calculate the steel area for torsion reinforcement using beam theory and add to the axial moment shear area on the section of a column? So, Matt, that is a great question. Matt is talking about if I have a column and it's got some kind of torsion on it. Now, Matt, I don't know if you've ever done torsion design for reinforced concrete. You probably have. And it's been a while since I have done it. But if you have like a torque happening on a column, then the best way, the most primary way that I've been taught on how to design for torsion is to increase your shear stirrups. Okay, your shear stirrups here. So the reason I bring that up is because you mentioned longitudinal steel. You mentioned steel here, 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 and here in a column. I've usually handled torsion using stirrups, using these things that hook and tie the bars together. That's how I've been taught to do it. And the way I've done it is I would take whatever I needed for shear and added to it whatever I needed for torsion. I don't believe, but it's been a while that I've ever increased the longitudinal steel because of torsion, but I could be mistaken. But if you're talking about shear stirrups, I think what you're talking about is totally appropriate and exactly the way I would do it too. Let's see. Biaxial wants to know, hey, thanks so much for the compliment. What kind of freelance work can we get as fresh graduates regarding analysis and design, and how to prepare ourselves for such projects? So I think freelance work is actually a little dangerous as a fresh graduate, because I think you want to make sure that you really truly understand what it is you're doing and how to do designs. So I think it's good to work with other people that are more experienced with you to make sure that you know what it is that you're doing, so you don't cause more problems, or cause problems in general. And so, but if there's something you feel very comfortable with doing, then I would say do it. And maybe you can find a more experienced engineer to check your work, or you could bring them on as well to look at something, and they would maybe be at a much, much, much lower rate. Another thing that you could do, I guess, is you could find someone that to actually mentor you, and you could pay them to mentor you. Yeah, pay them to mentor you. That's kind of what we do in school in a way. And so you would just find someone that, again, is very experienced, that you trust, that you can talk with, that you would pay them to answer some questions or help you with whatever design that you're trying to do. So you may be able to find people like that in the world. Man, okay. Class, if you've got questions, it's time to get them in here. I'm going to rapid fire some of these other questions here. So I've been in some structural drawings. L-shaped columns are used around corners, and T-shaped columns. Yeah, that's true. Why are they used, and why isn't it easier to have rectangular, circular columns? So what he's saying is that sometimes why do people choose using T's and L's? So I'm going to tell you, you have to do that. Get in the mind of the architect, and good luck with that. Also, because they make a lot of these choices. Sometimes mechanical engineers will make these choices too, because they'll want to run piping systems up and down these columns, and they think that it's causing problems if they run them on rectangular columns. I don't know why. I mean, seriously, I don't know why. I think they think they're being cute or something, or they're saving space. I don't know. I don't know. I really don't know, because it makes our life a lot harder. I mean, seriously, like a lot harder if they do that. And so you should ask them why they would do that, because I think they think they're probably trying to provide some value, but they may be making your life tougher. So just ask them about that. He says, can basalt, or he says grass fiber. I think he means glass fiber. Cable be used on pre-stressed applications? If so, how does the lack of ductility affect the design? I have never heard of basalt or glass fiber being used on pre-stressing. I don't think that's a good idea, because they're not ductile, and you're going to need to elongate them. So I've never heard of that, and I wouldn't recommend it. Great. How do I solve for AG? Hayden, give me some more questions here, brother. Give me some more detail on that. Are they PT or hollow core? They can be done either way, man. They can be done with PT. They can be done with hollow core. It doesn't matter. The only big difference between them is hollow core. They may do a whole long line of them, and then they may cut them. PT may be that they do them in place. They can do them either way. It doesn't really matter as long as they're well designed. You can use this system to do whichever you want. Simon wants to know, are synthetic bonding agents superior to neat cement paste when joining old concrete to new? Man, that's a great question. I wish I knew an answer. I think the answer is yes, but I don't know for sure, Simon. I've used both in the past. I would love to test both. I think a bonding agent may be a little bit easier to get right in the field than a paste, but I don't know for sure. And a sample prep, though, whenever you're using either one of these, is extremely important. This is like if you want to bond old concrete to new concrete, kind of like this type situation. If you want to increase that bond here, you're saying, can you use just paste down there, or should you use a bonding agent? I think bonding agents are better, but I've never tested them, so I'm not sure. Let's see. Let's see. So is it common to use post-tension structures as earthquake resistant? And I'm getting some sun, so I will move my overhead here as I try to answer this. See if that still works here. Yeah, it seems to kind of still work. Yeah. Anyway, so is it common to use post-tension structures as earthquake resistant? It can be. You just have to know how to design it. Some people are a little scary or scared of using post-tension structures in earthquake because they're worried about ductility. They're worried about the anchorage of those tendons, and so some people are have that concern. But I've seen them used before and I've seen them used really well in those cases and perform well. So if you can get your details right, then that will be great. Oh man, you just blasted me today. Can iron ore aggregate or iron tailings be used as a replacement for conventional aggregate in a concrete mix design? Oh man. I wouldn't allow any aggregate to be used inside a concrete structure that you really care about unless you have a performance history with that aggregate. And so I would be a little concerned about just using something that you didn't know how it performs. So I would look for long-term proof. Aggregates make up about 70 to 80% of your concrete volume, and that's just not something that I want to take a risk on. That's just my opinion. I think it could be done. I think you would just want to make sure that it has long-term performance. Yeah. So Mitzvah's saying he had no cracks permitted. Let me tell you a secret. The cracks are there. They're just small enough that you can't see them. They're still there. So to say no cracks permitted, it's not right. They're still there. You just can't see them anymore. So as long as they didn't see them, they were permitted. And fibers are a great way to do that. And watch for the video coming up. I can see you guys want to see the fiber video. LeBron coming back. The king. He wants to know why does curing not affect the water cement ratio? Well, LeBron, the short answer is that once the concrete sets, once a structure starts to form, adding water doesn't move the cement grains further apart. Adding water just promotes the reaction, promotes the hydration. I've got videos about this on curing. I've got videos about this on water to cement ratio and how it works. But the simple answer is once the structure is locked up, once the structure starts to form, extra water doesn't hurt it because it doesn't move those particles further apart. The key with water to cement ratio is it to be small so the particles start close together so they can grow together. If you increase the water cement ratio, it moves them further apart. So once they start to grow together, you actually want to add water to make that reaction go on. Sweet. That's really cool. Yes, Rihanna, that's exactly right. So Rihanna asked her question. I would treat this as a roller. I would treat this as a roller or a pin and a roller, um, and for this beam, and that way you don't have a lot of moment there. If you don't want to do that, you could treat this as a continuous beam, and you would do everything else everything I told you before. Everything would end up being the same. You would just have this would just look a little bit more complicated. But I would treat this as a pin and a roller and just put point loads there. That's the way I would work it. Okay, ladies and gentlemen. Let's see. AG, when in the phi capacity equation, similar to the example problem video you did. Okay, to the phi cap equation. Hey, I'm still not getting you, man. I'm still not sure what you're asking. Try again or email me. Alex has a question. So when we are calculating our gravity loads, do we just assume our trapezoidal tributary area to be a rectangle and use the same load per area? Yes, Alex, that's right. That's what I said in my gravity load video. That's what I recommended to do. That makes your structural analysis a lot easier to do, and it's conservative. Hey, Karen, how you doing? Ladle slag. Is there any potential method to activate ladle slag for use as binding material? Karen, I don't know for sure. I've not studied ladle slag a lot. The one simple way that you could study that or go after that or better follow that would be to actually put it in a sodium hydroxide solution and see if it reacts, see if it does anything, and that is a quick and dirty way to see if at least Portland cement will activate a ladle slag. But hey, thanks for the question. Yeah, University for seismic forces. Yeah, that's true. No open cracks. You're right. Yeah, didn't have fibers then, so we should use fibers today. Oh man, Simon, just pounding me, brother. What is the best way to practice heat of hydration in mass concrete? Well, Simon, it depends what you have locally. You can design your concrete mixture to have a lower heat of hydration. There is a computer program. There is a computer program for that I would recommend called Texas Concrete Works. Yeah, Texas Concrete Works. You can look up that computer program. It's a very, very nice finite difference program developed at the University of Texas by a gentleman named Kyle Riding and my former PhD advisor, Kevin Folliard. Anton Schindler, University of Auburn, he helped develop it as well, and also John Poole, who is a consultant now kicking tail out in the world. Go JP. But Texas Concrete Works is a very, very cool software package that helps you kind of evaluate different methods to minimize heat of hydration, minimize the amount of heat given off from mass concrete elements. But I would first design my concrete mixture with as little paste as I could and with certain binder types. There's lots of class F fly ashes that have a lot less reaction, heat of hydration, a lot of slags as well. Then what I would do if that wasn't enough still, I would try to use ice in my concrete mixture. Yeah, replace some of my mixing water with ice. Or if that's too expensive for you, another option is to use liquid nitrogen. Yeah, in a concrete mixture, in the concrete truck itself. Yeah, in the truck, concrete truck. It helps if you make like cool space noises when you draw the concrete trucks. In the concrete truck itself, they actually have this wand that goes inside that actually sprays liquid nitrogen inside. You can look it up. It cools the concrete down. It's totally amazing. It's very inexpensive once you get it set up. It's widely used in Texas, and New Mexico and Arizona. That is an amazing tool to cool concrete down for summer concreting or mass concreting. Or you can use cooling pipes inside your system and actually run water through them. That's commonly used in dams or other mass elements. So these are all techniques that you can use, and you can hire a professional that may be able to help you. All right, so I'm going to take 10 more minutes worth of questions. So if you've got questions, I'm going to try to go rapid fire here to these questions at the end. So if you've got them, and then we'll let the Beastie Boys play us back out. He wants to know about circular water tanks. Are very common, although we can get more volume with rectangular ones. Plus, we don't have to worry about hoop tension and save money on complex formwork. Well, no, you still, actually, that's not right. You still have to worry about the hoop tension for the rectangular ones. Actually, circular water tanks are much easier to design, have much lower stresses, and require much smaller members. If I have a circle, and if you don't understand, you should watch it's the same concept as in my barrel column video. I'm drawing the top view here, and I will go ahead and draw the inner lines of the circle too for a water tank. And if I have a rectangular water tank that would look something like this, when that water goes to fill it up, the same question is about like, why don't we use rectangular cups? Why don't we use rectangular barrels? Why don't we use rectangular anything to hold water? It's because you create huge stresses here at the corners, huge stresses at the corners that want to cause cracks. Reentrant corners cause cracks. This is a much more efficient. You need a much smaller, a much thinner member here, because the stress actually can be held much more efficiently by the hoops that go around the outside. So you'll see everything from grain elevators, everything circular as opposed to rectangular. So let's go back here. Aubrey wants to know what's the importance of surrounding temperature following curing. You want to keep your concrete to be consistent temperature if you can. You don't want temperature differentials. Man, if I was to design my own house, I've actually talked about this with my wife, and she doesn't want a concrete house. She says that I have concrete too much in my life as it is, and I don't need a house made of concrete. But let's just say I was going to design a concrete house. What would I do it with? I like ICF. I like preformed panels as well. I think ICF, if you've got a contractor that's experienced, I think that can be a great solution. I've seen constructability problems with ICF. ICF is where they actually have the formwork be insulating that you use for your concrete. So it's like cast in place concrete, like walls and columns, things that people already know how to do, but it has this kind of formwork that's insulating. Again, I think it can be great, but I think it can be challenging as well. If I had to choose which one, in where I'm at, I would probably go panels, because panels are more common locally than they are than ICF is. Hydration process. Watch my videos, man. I've got videos about hydration, or go watch something called Hydration Theater. Hydrationtheater.com. Yeah. Go check it out. Okay. So when water goes up due to bleeding, doesn't it affect water cement ratio? Sure it does. Yes, it does. So bleeding is when water comes out of the concrete, and it will reduce the water cement ratio of that concrete, but not by a lot. Not by a lot. And if your concrete's bleeding a whole lot, there may be something else wrong. You may have a mixed design concrete mixture. It shouldn't bleed a ton in modern concrete mixtures. But if the bleed comes out, it's no big deal. Reduces water cement ratio. I've never designed a concrete or steel silo, and so I've designed maybe one in my life, and they're not that hard. You just have to design for the stresses that I talked about before. These type of stresses, they're not that hard. So yeah, they're not that hard. So Alex asked about, are we factoring our loads or are we factoring our moments? So Alex, I will tell you, you can do whichever one makes most sense to you. One benefit sometimes to factoring moments. What Alex is asking about is there are load factors that we have, at least on LRFD type designs, of 1.2 dead plus 1.6 live, 1.2 dead plus 1.6 live. And there's wind, there's whatever. Alex wants to know, do I factor my loads or do I factor my moments? You can do either one, Alex. You could put your dead loads on your structure and find your moments from those dead loads. You could put your live loads on the structure and find your live loads from the moments. And you could factor the moments just like you factor the loads. It doesn't matter. It literally doesn't matter. Usually when you introduce a concept to somebody for the first time, it's easier to introduce it to thinking about factoring the loads and not necessarily factoring the moments. So that's probably why it was introduced to you that way. But you can do either way, whichever one makes the most sense to you. And you can email me if you have some more questions about that. Let's see. Sweet. Thank you from Serbia. I'm sorry you're an asphalt guy. It's all good though. I'm glad you have a passion. I'm glad you have a love. I'm glad you enjoy the videos. I would love, maybe we could trade some stuff back and forth. I think understanding both materials, asphalt and concrete, is totally beneficial. Yeah. So we did some nanoscale observations. Yeah, I've got some new stuff definitely that we need to get out there. We've got some new papers coming out about that, new work coming out about that. The funding on that research stopped, and so it's hard to make a lot of progress if you don't have a lot of extra money. But we're trying to get more to get things going. Sadly, in this world that I have to focus on, where my sponsors pay me to work, and nano hasn't been as popular lately. But there'll be more stuff coming on that. Yeah. What do you want to know about stainless steel rebar? I think it's a good thing. I think it can be good. I've talked about it in previous videos. I think it can be expensive, but I think it can be a good thing. I personally think galvanized rebar may be a better choice for a lot of different applications, but it just depends what you're doing. So Kieran wants to know about particle packing. And he's trying to try to activate his slag with acid. Did you try with a base, Karen? You should try with a base, not necessarily just an acid. And he wants to know, is there any software program to look at packing? There's software packages that are out there for that, but I don't know if I believe them. Yaks here. Good question. Let's see. So actually, the simple answer to your question here is, if when you treat a beam as pinned or fixed, what differences do you make in the detailing? So a fixed beam just needs to have steel wherever there's tension at the support. So if I have a column and I want to treat it as a fixed beam, then I need to design it to be a fixed beam. As in, I need to design tension steel up here, tension steel down here, tension steel down here. I need to just design for that. If you design for that, That is how it will behave. Let's say you don't. Let's say you leave those bars out. That is how it will behave. That means there's tension here, but there's no bars there. It'll just cause cracks there. If the loads are small, the cracks will be small. If the loads are large, the cracks will be large. And you might say, I know this is probably strange and hard to understand, but the more you understand about concrete, the more you understand, truly deeply understand about concrete, is that you can control where your loads go by where you put your reinforcement and how you think about your design. This is kind of the secret to something called strut and tie modeling. And with more study, you can kind of better understand how to handle these out of the ordinary situations. But I know that's probably a bad answer, but there you go. Yeah, definitely. Formwork is very expensive. Okay, I see about 2 more questions left. For precast building structures, how are different precast components connected together to ensure moment transfer? What do joints look like in precast buildings? So, Hassan, I cannot answer this super quickly. I think it's going to just depend. I'll try to give you a general answer, though. It's my last piece of paper, so this will be it. The last question. So it is common in precast type systems to I got actually 15 thumbs up. Hey, if you haven't given me a thumbs up, then you need to. You need to slam me a thumbs up in the wherever you possibly can to let me know that you like this. So I apologize for the light here. I mean, I can move this up a little bit here. Maybe I'll have a little bit less underneath here. So Hassan, this. Here we go. It's common. I may have a column down here. I may have a bearing pad, some kind of temporary bearing pad that's put in place here and here. I may put a beam. A beam may go here. A beam. And a beam here. This is commonly used in California, this type system. And I'm assuming you want it to be moment transfer. So we're going to assume seismic detailing here. So what's going to happen here is that you're going to take your rebar out of your column rebar. Rebar's not helping me here today. We'll try this picture, see if this is a little bit better. Rebar. You may tie another set of rebar here in the topping slab, and then you're going to cast all of that in concrete. All of that joint is going to go cast in concrete. So when you fill in the deck, when you fill in the topping slab up here, you'll fill in this and this and this, all of it together to create one strong connection. You're also going to have steel that may come out of the beam that ties into this, right? That's something that you could do. Maybe you might say, oh, that doesn't look very good. Okay, I probably didn't draw it right. The point is that you maybe need to make your columns wider. You need to allow your beams, these are pre-stressed, precast, pre-made pieces. These may have bars that stick out. This is going to have bars that stick out. You may tie those together to make some kind of core out of that. You might put stirrups in here, and you might pour concrete in there. You might say, wow, that looks hard. That looks like that's congested and weird and tough. Yeah, it is. Seismic detailing is all of those things: congested, weird, and tough. So, yep, Mitzvah, that's correct. Virginia, all bridge decks are stainless steel. That's exactly right. They are. I'm a big fan, and I like that they've decided to do that. But in a lot of other states, like Texas and many other states, they find that stainless steel bar are too expensive for them. I'm fine with stainless steel. I don't have a problem with it. I think it's a great solution if you want to do it in your local area. I think galvanized is a little less expensive, and I see really good performance out of it. So you can watch my video about why is epoxy coated rebar being banned, and I talk about some of these concepts in that video. Hey, thank you everybody, and we'll go from there. I really appreciate it, and I'm not sure if we're going to have a session next week or not, because that's actually during my final exam or the day of my final exam, and so we'll see. But I'll probably do one next week, maybe on another day. We'll see. Or maybe I'll end up doing it at the same time. I'm not sure yet. Take care, everybody. Oh, there's one question here. I'm on ACI 209's recommendation for modeling ultimate shrinkage of concrete. So I am not a fan. I don't think it does a very good job, in my opinion. I think it's got lots of problems. At least maybe it does what it does well, but I think there's some problems with it, big problems with it. Is a pass or fail parameter for judging whether shrinkage is manageable. So I'm a big fan. I use 300 microns as the number, 300-ish microns at 28 days of drying shrinkage. That's kind of the number, I think, or 28 to 90 days of drying shrinkage, depending on what you want to do. That's what I use. And I've seen lower numbers, and I've seen a little bit higher numbers, but right around in that range. That's what I see. Hey, everybody, take care. It's been fun. We'll let the boys play us out here.